Good evening to everyone. I'm Cecilia Toccaceli, and for this work, the goal is to propose a family of opinion dynamic model to study how specific social interaction patterns contribute to the acceptance or rejection of fake news by a population. First of all, let's define what a fake news is. We can define them as news articles that are intentionally and verifiably false and could mislead readers. Well, we have chosen to use a continuous modeling framework extending the Exelman-Krauss model, and this model is characterized by the bounded confidence, called epsilon, and at each iteration, an agent is randomly selected, and this updated opinion becomes the average of its neighbor opinion in epsilon. This because agents can only interact if their opinion differ up to epsilon. We modify the starting model by adding stubborn agents that are individual with fixed opinion, and during each iteration in our model we consider a random pairwise interaction. In the model called weight HK model, we add age weight to capture the strength of the different social bonds, so the new opinion of the selected agent will become the weighted average of his previous opinion and the opinion of his neighbor. We then define the attraction WHK model, and it simulates an interaction between two agents who agree on a given topic, and at the end of the communication, their opinion will be closer. The updated rule provides a different formula depending on whether the opinion of selected agents are discordant or not. So in this way we can guarantee that the difference between their respective opinion is reduced after communication. However, when observing real phenomena, we can identify situations in which interacted individuals move away from those who have opposite opinions. We model this scenario in repulsive WHK, and in this case, the updated opinion of selected agent ensure a greater distance between the opinion of interacting individuals. The attraction-repulsion WHK model considers both effects. In this case, two random agents are selected, and if the absolute value of the difference between their opinion is lower than epsilon, attraction WHK is applied to compute the new opinion of the selected agent. Otherwise, we apply the repulsive model. We simulate the model on mean field, random network, and scale-free network, varying epsilon and the percentage of stubborn agent in the network. These plots show the opinion evolution of each agent, and different colors represent the agent's initial opinion, positive, negative, or neutral. For the attraction model, we can observe the same result for all different topology. In fact, the increase of the bounded confidence results in a more chaotic regime, while stubborns act as persuader, bringing the opinion of the population closer to theirs. For the attraction-repulsion model, in scale-free network, in this, we observe a fragmentation into cluster of opinion with the central group which tend to disappear by increasing epsilon. While in random network, this, when epsilon increases, the opinion group tend to converge into a single one, similar to consensus. To simulate a more realistic network topology, we also tested the model on a network generated through the LFR benchmark, and for this case we used the network visualization instead of opinion dynamic plot. The node with positive opinion are shown in red, the one with negative opinions in blue. The darker the shade of color, the more extreme opinion. In this slide we can see the initial configuration of the network that consists of 4 communities, and using the attraction model we can observe how the resulting final equilibrium converges toward a common spectrum. In this case, stubborn can make their opinion prevail even crossing community boundary. Conversely, applying the attraction repulsion model, the final scenario presents two strongly polarized community, and in this situation stubborns increase the polarization of their community and make rare cross-community ties. Studying results of experimental analysis, we can conclude that the differences in the topological interaction layer reflect on the time to convergence of models. Then stubborns influence the final scenario, especially using an eigenvalue of epsilon, and the attractive interaction fosters the achievement of common opinion in the population, while the repulsive one facilitate polarization. Regarding future research, we propose to apply the methodology on real data, and we plan to investigate the effect of higher order interaction on opinion dynamics. Thank you all for your attention.